In this video, we're going to talk about combinations. This is the number of ways to select k objects from n objects where order doesn't matter and repetitions are not allowed. So in the last video, we looked at n permute k and saw that that was the number of ways to select k objects from n objects where order does matter and repetition is not allowed. So we saw that that is npk, or n permute k, was equal to n factorial over n minus k factorial. And we could also just get that through the multiplication rule, saying that there are n choices for the first element and n minus 1 choices for the second element, since we can't repeat, and dot, 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 all the way down until we've chosen or selected k objects. So what about situations where repetition is not allowed? That's the same, but order does not matter. So this is different from a permutation. So for example, if we were asking how many different 5-card poker hands are there from a standard 52-card deck, this would be a situation where it's a hand of cards. You know, you've got your hand of cards in front of you. So here order doesn't matter, and if it's a standard 52-card deck, you know, there's only one card of each type. There's no repeats. You can't have two of the same card. So in this situation, let's think to something we already know how to do and see if we can gather this new idea from it. So if our question was, instead, deal 5 cards from a deck lined up in a row, otherwise ordered, how many such lineups are possible? So this would be ordered, and again, no repeats. And so that means that this would be a permutation. This would be 52 permute 5, which is 52 factorial over 52 minus 5 factorial, or 52 factorial over 47 factorial. And that could also be written as, just using the multiplication rule, there's 52 choices for the first card, 51 choices left for the second, 50 for the next, 49 for the next, and 48 for the next. So we could either use that formula, 52 permute 5, or the multiplication rule, and simplify that to find our answer. However, again, this is assuming that these are ordered. So we do know that the number of 5-card lineups, these are ordered, is equal to 52 permute 5, or 52 factorial over 52 minus 5 factorial. Now what we actually want, we want the number of 5-card poker hands. These are unordered. And how could that relate to what we already know, to a permutation? Well, the number of ordered 5 cards should be equal to the number of 5-card hands that are unordered multiplied by the number of ways to then order those 5 cards. So this equality should work. The number of 5-card lineups should be the number of different 5-card hands that are unordered times the number of ways to reorder those 5 cards. So let's use that and then solve for the thing that we want. So let's solve for this. So the number of 5-card lineups is 52 factorial over 52 minus 5 factorial, and that's equal to the thing that we want, number of 5-card hands multiplied by the number of ways to order 5 cards. We know that the number of ways to rearrange 5 objects is 5 factorial. And so this tells us then that the number of 5-card hands, the unordered number of 5-card hands, is 52 factorial over 52 minus 5 factorial divided by 5. So we're going to divide both sides by 5 factorial, divide by 5 factorial, and so we're left with 5 factorial in the denominator there. So the number of 5-card poker hands that are unordered, where again, no repeats, is 52 factorial over 52 minus 5 factorial times 5 factorial. So in general, we had n equals 52 objects to choose from, k equals 5 objects, 5 cards, and so what we have here is n factorial divided by n minus k factorial, that's just the permutation part, and then divide by k factorial, the number of ways to rearrange those k objects. So in general, the number of ways to select k objects from n objects where order doesn't matter and repetition is not allowed is n choose k. So this is pronounced n choose k. It's often written with these parentheses, n and k over each other in parentheses. N choose k is equal to n factorial divided by n minus k factorial times n times k factorial. And just remember, this is like the same thing as n permute k, the number of ways to select k objects from n objects where order does matter, and then divide by k factorial, the number of ways to order k objects. So this is also equal to the number of subsets of size k that are possible to create from a set of n objects, and that makes sense. Order doesn't matter in a set, so if we're talking about number of different subsets, the subset A, B is the same as the subset B, A, and there aren't any repeated elements, or if you throw another object that's the same into the set, it just stays the same. So yeah, order doesn't matter, no repeats. That means that this is a combination, or this is something of the form n choose k. So for example, how many subsets of size 3 are possible from the set A, B, C, D, E? I'll just pause briefly. I'd like you to find this using the formula and also simplify your answer. So find and simplify your answer for this problem. Okay, so the number of subsets of size 3 that are possible from the set A, B, C, D, E. Here n, the number of objects to select from, is 5, and k, the number of objects that we're selecting, is 3. Again, no order and no repeats, and that makes this a combination. And so this is nck equals 5 choose 3 equals 5 factorial over 5 minus 3 factorial times 3 factorial. Now simplifying this, we've got 5 factorial divided by 5 minus 3 is 2 factorial times 3 factorial. And factorials simplify it nicely. So here we've got 5 times 4 times 3 times 2 times 1. Notice that is 3 factorial. Over 2 times 1 is 2 factorial times 3 times 2 times 1 is 3 factorial. We can then cancel out the 3 factorial with itself. And so we're left with 5 times 4 over 2 times 1. We can cancel some more. We've got 2 left, and so we've got 5 times 2 is 10. So 5 choose 3 is 10. Here are just 2 quick other ones that are not necessarily combinations. So how many lists of length 3 are possible from the set A, B, C, D, E? And how many lists of length 3 are possible from that set if the elements cannot be repeated? So pause briefly and try those out. Okay, number of subsets of size 3 that are possible. We already calculated this one. This was 5 choose 3, and we found out that that was 10. 5 factorial over 5 minus 3 factorial times 2 factorial. Number of lists of length 3 that are possible from this set. So it's a list of length 3, 3 elements. That means it's ordered. So this is ordered. And it doesn't say that repeats are not allowed, so we should assume here that repeats are allowed. And so there are 5 choices for the first element and 5 choices for the second and 5 choices for the third. This is and, and therefore we use the multiplication rule. So there are 5 times 5 times 5, or 5 to the third possible lists of this size. Note, if this is n and this is k, as we've been using, this is n to the kth power is the number of lists of length k from n objects. How many lists of length 3 are possible from the same set if the elements cannot be repeated? Well, again, we've got a list. It's ordered, and now there's no repeats. So how many possibilities are there? There are 5 possibilities for the first and 4 for the next, because we can't repeat, and 3 for the next. This is 5 times 4 times 3, using again the multiplication rule, or we could also use this, write this as 5 permute 3, which is 5 factorial over 5 minus 3 factorial. Again, canceling out would give us 5 times 4 times 3 times 2 times 1 divided by 5 minus 3 is 2 factorial times 2 times 1. And so, of course, yes, it would give us the same thing. This is 60 if we multiply it out. This 5 to the third, if we multiply it out, is 125. Again, just to get a pattern here, still we've got n is 5, k is 3. This number of ways to select k objects from n objects with no repeats where the order matters is n permute k, or n factorial over n minus k factorial. So let's just write all those down together. The number of ways to select k objects from n objects is, if order matters and repeats are not allowed, it's n to the k. That's using the multiplication principle. So using the multiplication rule or the multiplication principle, there are n choices for the first object, and so multiply n choices for the next, and dot dot dot, n choices for the last object, and there are k objects altogether, so that's n to the k. If we have a situation where order matters and there are no repeats, we've got n choices for the first object and n minus 1 for the second, and dot dot dot, n minus k plus 1 for the kth object. This is the same thing as n factorial over n minus k factorial. Again, this really comes from the multiplication rule. And lastly, if order doesn't matter and no repeats are allowed, then we can take what we had before, n times n minus 1 times dot 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 times n minus k plus 1, number of ways to select k objects where order matters and no repeats are allowed, and divide that by k factorial, the number of ways to reorder those objects, because we don't care about the order. And so this is the same thing as n p k over k factorial, and this is n choose k.